Hello there. This talk is going to be about an obstacle problem for the p-elastic energy, which I have studied in a joint work with Anna Dalakwa from Ulm and Shinya Okabe and Konsuke Yoshizawa from Tohoku University. So I will define what the problem we study is in a second. First of all, of course, I have to say another time thank you to the organizers of the Geometric Analysis Festival and for the opportunity to speak here. So what is the variational problem we study? We look at the following energy, the p-elastic bending energy that assigns to a function u, like a suitable smooth function u, the curvature to the power of p of the graph curve that is associated to u, integrated to the power of p over the curve. Basically, this is a curve integral. And this measures basically how much this graph curve of u bends. So weighted with a power of p. P can be arbitrary between 1 and infinity. Okay. And graph u, just to clarify, is the curve that assigns an x to the value x u of x in r squared, right? So it's a planar curve. And the obstacle problem we are now looking at is we minimize this energy. If you write out what this basically is, it is nothing but u prime prime to the power of p over a denominator that involves only the first derivative. You minimize this energy among all functions in W2P such that you have fixed ends. So basically you connect two fixed points with this curve. And you have an obstacle constraint, so you require, and this makes an obstacle problem out of it, you require that you lie pointwise over an obstacle function, and you have some constraints on the obstacle function that you impose. Namely, the obstacle function is supposed to be continuous, and it's supposed to be non-trivial, because if this is negative, for example, you could take easily the function u identically equal to 0 as a global minimizer. This we do not want to allow. This is why we require that psi is not small or equal to 0. But at the boundary, I impose that the obstacle is in a way not present, that it's negative, and therefore we have no further conditions on u at the boundary except for this fixed ends condition. And other than that, this u may vary freely in a certain neighborhood of the boundary. Okay, this is the obstacle problem. Those two are our constraints, and then we can try to minimize. And the question is, of course, how to describe the minimizer, and the answer is a little involved already, because whenever I'm above the obstacle, whenever a minimizer is above the obstacle, as you can see here in the yellow regions, that can happen. Then you have every perturbation for this minimizer is possible so that it stays admissible, and therefore on those sets where a minimizer strictly exceeds the obstacle, you can describe the minimizer with an Euler-Lagrange equation. But on the other regions where you hit the obstacle, there you cannot describe the minimizer with an Euler-Lagrange equation anymore. And the reason is that you cannot perturb in every direction as if you hit the obstacle, right? So if you perturb the minimizer in a downwards direction, it would basically go out of the admissible set, and therefore you might lose the Euler-Lagrange equation and therefore lose the regularity that is associated with it at the point where you touch the obstacle. And this tells you that you have a free boundary in this problem, namely the interface between the non-coincident set and the coincident set. This is the free boundary of the problem. You have to know that in order to be able to describe the minimizer, and this imposes a difficulty, and this is basically the spirit of all obstacle problems. Wherever you are bigger than c, you know that you satisfy the Euler-Lagrange equation. But on the coincidence set, you basically know nothing except for that you coincide with the obstacle. Okay, one thing you can derive that will be relevant later is, however, an Euler-Lagrange inequality. So if you perturb with a positive function, then basically you stay always in the admissible set, right? If you perturb in upwards direction, perturbations still stay admissible, and therefore you get an inequality because you can now perturb in the positive direction and stay admissible, and this is why you get this inequality. So this is as close as you can get to an Euler-Lagrange equation with the additional information that you know that your critical point wherever the obstacle is not touched. Okay, so what are the challenges that this energy imposes on us? First challenge is this energy is non-coercive, and this is because of this denominator there that can basically ruin the coercivity in W2P. And the second challenge I already talked about is the loss of regularity at the coincidence set. And the third challenge, which we haven't talked about yet, but which is also relevant, is the degeneracy of the Euler-Lagrange equation in the case of P is bigger than 2. And what do I mean by that? If P is bigger than 2, then, for example, we can maybe look at a similar but sort of simpler energy. Energy equals u prime prime to the P minus F times u integrated for some smooth F. And then we can compute the Euler-Lagrange equation, and it's going to be this Euler-Lagrange equation. And the question is, will such an equation have regular minimizers? And the answer is unfortunately no, or in general no, because it is degenerate elliptic. So this is basically the ellipticity of this term here determines the ellipticity of this operator that is associated to this equation, and it can degenerate, namely whenever u prime prime equals 0, and u prime prime equals 0 has in our curve interpretation a certain interpretation, namely that you might know that the curvature is also u prime prime over 1 plus u prime squared to the power of 3/2. So basically u prime prime equals 0 is vanishing of the curvature. And when you have a point where the curvature vanishes, then you might experience a degeneracy of the Euler-Lagrange equation. And this might be a huge problem for regularity analysis. And the other huge problem is maybe also that it's of fourth order, so no maximum principle is available for such an equation. Okay, so this is the problem with degeneracy. It can occur for this equation as well, that at the points where u prime prime equals 0, we have a degeneracy of the equation, at least if p is bigger than 2, like the ellipticity of the equation that guarantees regularity degenerates. Okay. So those are the challenges. Maybe we should also say some properties of the minimizers before we start examining whether the challenges can be overcome or not. If we have a minimizer in the admissible set, I will write the admissible set down later, then it is always concave. Why is that? So if you take any admissible function u and you take its concave envelope, which means you replace the convex parts by lines, then you lose energy. Because if you replace those parts by lines have curvature equal 0, so they have energy 0. So basically you decrease the energy by taking this concave envelope, which is here in orange, but you still stay above the obstacle, since this concave envelope always lies above the comparison function. and therefore you basically can decrease the energy by forming the concave envelope, and therefore you can conclude that your minimizer must be concave. This is a very important property. And the other property is that minimizers have natural boundary conditions in a way. So we only required up to now that the two boundary conditions, namely that we fixed the ends, right? So we fixed u of 0 equals u of 1 equals 0. But for a fourth order equation, we basically can fix 4 conditions, and therefore 2 conditions come up naturally. And this is that the second derivative at the point 0 and 1 also vanishes. This is again because the obstacle is not present at the boundary, and therefore you may vary freely at the boundary. So there's no reason for minimizers to have curvature at the boundary. They really don't want to collect any curvature at the boundary because this is not energetically useful. So they rather say that they won't curve at the boundary. And this also comes with a regularity statement that can also be of use. We know that all those minimizers are C2. Okay, so those are 2 properties that will be of importance later, and this is why we discussed them here. And now the question is, can we always find a minimizer U star that is admissible with respect to psi? So admissible with respect to psi means it comes from a W2P graph that also satisfies u of 0 equals u of 1 equals 0. So this is hidden in the boundary conditions, and that satisfies pointwise that u is bigger or equal to psi. Notice that I can actually evaluate this u pointwise because W2P embeds into C1 by Sobolev embedding, and also at the boundary points this can be evaluated. Okay, so this is the question, and here's the answer. So for small obstacles, there exists a minimizer, but if the obstacle becomes too large, minimizers stop existing. And we will now, in the videos that we will discuss, only focus on why minimizers stop existing if the obstacle is too large. And I should mention that all of this has been studied in previous articles for p equal 2. So those are also interesting to look at. And we will see why this can also hold for arbitrary p in 1 and infinity. So why does this hold true? Here in this video we will try to look at the geometry of the problem, and we will find the right class of obstacles for which we can obtain non-existence. To this end, we look at symmetric cone obstacles. So what are symmetric cone obstacles? Basically, you see them here. They are supposed to be symmetric around 1/2. And between 0 and 1/2, they have to be affine linear. So there they just have to be a line, basically. Those are the obstacles that we consider here. And why is it advantageous to consider them? Well, because I know for those kinds of obstacles the coincidence set. I know that the obstacle is touched only at 1/2, only at the tip of this cone obstacle here. So all our minimizers will look like so. So they can touch the obstacle only at the tip. And why is that? Well, if I would touch the obstacle somewhere other than the tip, then this will almost contradict the concavity, because if I touch a line from above, I need to do it in a convex way. So that one can maybe see here a little. And this cannot be true if the minimizer is supposed to be concave. Okay, here one can say it can still technically be true if the minimizer has a line part there. So this one also has to exclude separately. So this argument that we have here is not complete, but maybe it is geometrically convincing that the minimizer can be only touched at 1/2. Okay, or that the minimizer can only touch the obstacle at 1/2. Okay, so now we know, since we know where the coincidence set is, we know how the minimizer can be described. Namely, between 0 and 1/2 and 1/2 and 1, I have critical points, so solutions of the Euler-Lagrange equation. And those two match together at 1/2, and there I have to touch the obstacle. This is basically a complete description of possible minimizers, and this is great since one can then say whether minimizers exist or not. Okay, so in the special case of p equals 2, this existence problem for minimizers has already been solved, and I can show you the minimizers now. So the red one will always be the obstacle, and the blue curve will always be the minimizer. So if I have a small obstacle, I get such a minimizer, and if the obstacle is larger, I get a larger minimizer, and if the obstacle is even larger, I get an even larger minimizer, and so further and so forth. I could keep going forever, but at some point here, one sees, even in the case of p equals 2, that one encounters a problem. And the problem is the following. At a certain height, h star, the minimizer develops vertical slope. So basically its derivative becomes infinite at the values 0 and 1. And this is really problematic because we know our curves need to be, that we consider or that we look at, need to be graph curves of a certain graph u. And u, however, needs to have bounded derivative because it's in W2P, and therefore this cannot be a minimizer anymore. So if you look at those minimizers for p equals 2, if you look at those explicit minimizers, let's say, then they develop a vertical slope at this value h star. And this is of course a problem for the existence results, since there at this h star and above also no minimizers will exist. And this is the whole point behind this non-existence. Minimizers will lose their graph property and develop vertical slope. Okay, and now we can ask, at what point h star does this actually happen? What is this h star? Does this number here between 0.8 and 0.9 have a special meaning? And yes, it does. It is namely the height of the inflectional free elastica, which is a critical curve that already Euler found. It's a critical curve of Euler's elastic energy. So this is basically the energy that we are looking at, but now for arbitrary curves and not for graphs. So the energy we actually look at is basically this energy. So the energy is this curve energy of the graph of u. So this energy basically has a critical curve whose height is exactly h star, namely exactly this gamma star. You have a distance of 1 here, and the height of this critical curve, is exactly h star here. So this is how this theory can be connected, is connected to this curve energy, and one has to study maybe what this critical curve here has to do with it. What Euler already knew about critical curves of this energy is that this gamma star is the only critical curve of this energy apart from the line. So the line as a global minimizer is also a critical curve, but also this gamma star is a critical curve. And further than that, one can only have scalings or isometries of this critical curve gamma star. So isometries is rotations or translations, right, in the Euclidean plane r squared. There you can have only these kinds of isometries, rotations and translations. And then you have an exhaustive classification of critical curves here. And this exhaustive classification of critical curves of W will really lead to the following non-existence result. So if C is a symmetric cone obstacle and has height above this exactly this H star, then there does not exist a minimizer. And the reason for that was very sharply understood, or understood in a very sharp way, by Tatsuya Miura in this article. And I will show you the proof of this theorem, basically, that he gave. So one can prove rigorously that above this H star, one has non-existence of minimizers. And the reason is the following. So let's assume we have a minimizer that is in this admissible set M of psi. And so that lies above psi. And for simplicity, we assume that it's symmetric. One can repeat the same argument if the minimizer is not symmetric, but I will not go into details. We assume that here only for simplicity. And then we know either this minimizer, so this minimizer has to be a critical point also of the curve energy in a way. So it just has to be either a line, or it has to be, so between 0 and 1/2, it has to be a scaling or rotation of a certain part of this gamma star, right? Because those two curves are the only critical curves of this curve energy. So U star between 0 and 1/2, which had to be a critical point, now has to be one of those two types. And lines are not allowed, because lines can never have a derivative of 0 unless they are completely straight. And the problem with that is then I cannot exceed the obstacle, right? It is not possible to exceed the obstacle with a line that has derivative 0. So basically the line case is excluded. So now all I'm left with is I know that the minimizer must consist of a scaling and a rotation of a part of this gamma star. So I need to choose a scaling parameter, a rotation angle, theta, that actually is smaller than 0, because I may rotate this gamma star only to the right. Because if I rotate to the left, then I would immediately lose the graph property of this gamma star, because it has vertical slope right here. So I need to rotate it to the right, and I need to cut it somewhere. So I have those three parameters: optimal scaling, optimal rotation, and optimal cut. And how do I get a minimizer with those three parameters? Well, first I have to take gamma star. So this is gamma star, and I have the blue curve, and I cut an orange part out of it. Then I need to scale it, and then I need to rotate it in such a way that I exactly hit the obstacle at this point 1/2 here. So if this is 1/2, I need to hit the obstacle there. And that way I only need to choose the optimal cut, the optimal scaling, and the optimal rotation. That's the three parameters I have here. And I also have three conditions, basically. First, the two-dimensional condition that the obstacle needs to be touched at this point 1/2. And the second condition is that the derivative here has to be vertical or horizontal. Horizontal. I have those three conditions. The derivative is 0 there is because of the symmetry. But if one doesn't assume the symmetry, you just get an inequality there, and you can check that it all sort of works out. I'm not going into details here, but also you need to touch the obstacle at this point. So you have three conditions basically, and those three conditions can be easily written if you take complex arguments. So if you go into the complex numbers and identify r squared with the complex plane, you can now basically compare the arguments, like the complex angles. So the complex angle of this expression is basically the argument of gamma star of A plus theta, the rotation that you get. And here you get the information that theta plus the argument of gamma star prime must equal 0. That is how, if you also write this equation with complex arguments. And with those equations, you can eliminate theta here, because you have an explicit expression for theta, and you only get something that only involves A, basically, namely the argument of 1/2 and psi1 of 1/2 transposed has to be equal to this difference. And this is actually great, since now one can solve this for A, or one can look at whether this has a solution for A at all, like it's just a one-dimensional problem now. And if it has no solution for A, then we know that we cannot find a minimizer. And indeed, this will be happening, that we have no solution for this equation if psi of 1/2 exceeds this H star. Okay, and so how Tatsuya Miura found a very, very geometric way to prove this. Namely, he looked at the so-called polar tangential angle. This is basically exactly this quantity, the angle between the curve and its derivative. And so one can look at this polar tangential angle between curve and derivative, and one can see that it's a monotone quantity under a certain condition, namely if the product of the curvature and the derivative of the curvature of such a smooth immersed curve, if that doesn't change sign, then the polar tangential angle is a monotone quantity. So this is a monotone quantity, and this explicitly characterizes when such equations are solvable or not. And this is what is taken advantage here from. Okay, so that is the proof, basically. We can therefore exactly say when it does not have a solution, this equation, and this is why also this result is sharp. And now we can try to repeat this technique for the case of p equals between 1 and infinity. So for p between 1 and infinity, we have this energy to consider. And what we dream again is that each critical point is either given by a line or some inflectional p elastica. So again, a curve of this type, maybe now being a little different with different p's, but still be having this inflectional property and having sort of the same properties as this gamma star that we used before. And why do we dream about this? Because why do we wish for this? Because this actually makes the proof of Tatsuya Miura there more generally applicable. If this is again an exhaustive classification of critical points, then we can indeed repeat the same analysis. And we can indeed find again a sharp non-existence threshold. So this would be great if we could do that. If we find out about such a result, but we have a problem. Namely, for p bigger than 2, we can have much less regular critical points, and this is again because of the degenerate ellipticity, where we lose the ellipticity where the curvature vanishes. And therefore, it can very well be that we have much more critical points, that the situation is much more highly non-unique than in this setting. And the reason for this is this degeneracy when p is bigger than 2. So one can also see it when looking at the Euler-Lagrange equations For the curvature explicitly, or for this curve energy explicitly, those look like the orange one, and here we see that it's an elliptic operator with a very degenerate coefficient here, at least when the curvature vanishes. So yeah, we have a problem when the curvature vanishes, because what can then theoretically happen is that we can get type 3 critical points. So type 3 critical points, so type 1 critical point is maybe the line, type 2 critical points are maybe those gamma star p, which also exists definitely as a critical point, and type 3 critical points are now possibly combinations of those two. And I can actually combine them, since I lose ellipticity on the set where the curvature is 0. So I could combine a line where the curvature is 0 with a part of this P elastica, and it could be critical. I don't know. For p equals 2, one would immediately say, no, this cannot be critical, because the Euler-Lagrange equation is analytic and elliptic, and so this cannot happen. But now that it's degenerate elliptic, we really have to take care of this type 3 critical points and have to exclude them somehow, because if we have those type 3 critical points, we cannot repeat the argument of Tatsuya-Miura I just showed you, because if that's not repeatable, that would of course cause some problems. Because then if there exist such type 3 critical points, we have also to take into account that such pieces could maybe make or be part of minimizers, and one really has to study that more carefully then. So how big can this set kappa equals 0 be for critical points? If one can show that it's only a singleton, then maybe there's nothing to worry about. But in fact, with fixed length assumption, there was already constructed a critical curve for this WP energy, for this P elastic energy, namely by Watanabe. But under this fixed length assumption, which is therefore a different context from ours. But anyway, with this fixed length assumption, you find such a curve that has curved parts here and combines them with a flat part where the curvature vanishes, and one calls those flat core critical points. And those can really, really occur in such a case where P is bigger than 2, so Watanabe has classified them, that they can, and has observed that they can occur. And the question is now, can we still be lucky? Is it still possible, now that we have this example of a flat core critical point, is it still possible that the second derivative will not vanish in the interior for our, like that we don't have to take into account like flat core critical points? And maybe to convince you of that, we look at this more simpler energy. And if we look at the Euler-Lagrange equation of this is that. We have already computed that basically in. If one looks at this equation, one sees that an immediate consequence is that u prime prime to the p minus 2 times u prime prime has to be a line there. And now lines only vanish at maximum one point, or they vanish always. So either u prime prime is identically equal to 0. This is now corresponds to the line case, but each critical point that is not a line, that can only, the vanishing curvature set can only consist of at maximum a singleton, and this of course gives a little hope for what is about to come. So maybe it is possible, if the energy is maybe a little more like this, then it is possible to exclude those type 3 critical points, and then it's possible to repeat the analysis of Tatsuya-Miura. And spoiler alert, we will be lucky and we can show that for minimizers no type 3 critical points can take part in the minimization. So if I take a minimizer, then one can show that the second derivative is strictly smaller than 0 between 0 and 1, and this is rules out basically all those type 3 critical points. And we will see this result or a proof of the result in the next video. And so type 3 critical points are not allowed, and we only have type 1 and type 2 critical points, so lines or like this inflectional p elastica. And therefore we can repeat the arguments here that we just saw with the polar tangential angle, and therefore we can obtain that if our obstacle is higher than the height of like such in inflectional p elastica, I call this h star of p, then one obtains a non-existence result, then there cannot exist a minimizer in M of C. Okay, so if you want to learn more about why this second derivative is strictly smaller than 0 in the interior, then we will talk about that in the next video. See you then.